And Augie, if you are there, we are ready for you.
Okay, and that would be here. Okay, this is coming about because Ed Dower, who's running a small group of individuals who are involved in SETI, the search for extraterrestrial intelligence, thought that it might be interesting to see if there was any kind of a nexus with your group and possibly have some people who are in your group who are interested in SETI also join us, and vice versa. And I'm happy to be being a part of both of those, and intend to, as I say, I'm signing up for both for membership as soon as I get that completed. I had to work on a few other things first. In any case, what is SETI? I think is the first thing we have to answer, and it's the search for extraterrestrial intelligence with the emphasis on intelligence. Now, it also involves many other things. The SETI Institute was formed a while back, and I'll go into just a very brief detail on that. But there are scientists who are doing experiments in lots of different fields related to the search for life elsewhere in the universe. And the emphasis is on the intelligence part. However, it's nice to know that there are planets in what are called exoplanets associated with stars out in the Milky Way and elsewhere that have planets going around them that have exobiology as a first step. You got to have that before you can have intelligent life, and then intelligent life has to live long enough to become technology experts and be able to send and receive signals. They're trying to answer the big question, which is, are we alone in the universe? However, um, the Fermi paradox has been stated that if we're not alone, is there any evidence for it? Where is that evidence? And precious little has been found, if any, that is reliable. And so the search continues for that. The question that I have asked a couple of times with the SETI folks is, if everybody's listening and nobody's transmitting, that's kind of like in ham radio. I'm a ham radio operator. That's a dead band situation. The band may be fine. There may be the ability to transport signals, but nobody's sending. And if nobody's sending, nobody's hearing, and there's no communication. So we need to be able to resolve whether we're going to be able to send signals or not. Funding for SETI, by the way, started in November of 1984. The NASA folks had a fund that they as part of their funding from the government. They had a SETI group. It wasn't terribly active, but there was NASA SETI before the SETI Institute came into being. And funding was split off from NASA, a small portion of it, to run the original SETI Institute. And by February of 1985, with the NASA funding and some additional private funding, the Institute kicked off and started doing its work. As of 1993, the government decided to cut off the NASA SETI program. The funding for that is gone. And so now SETI is entirely funded by individuals and organizations who make grants and donations to the cause, but nothing is coming through the original funding from NASA. The regional SETI focus groups is an idea that Edward Dower had, and he started a group about a year ago, maybe a little bit more than that. And that's myself, my wife is involved in it also, and two or three other individuals. And we're looking to bring a few more people in who may have common interests with us. It's kind of like a book club, as I note here. And that is, if you've ever been involved in a book club, you read a book, you get together some night, talk about the book, and have a conversation and try to figure out what each of you came away with from that. And we have a feeling that in the SETI arena, the same kind of thing can happen. So that's what this is all about. Most of our members, myself and Ed in particular, but a couple of others also, have telescopes, and we've done visual astronomy long in the past, in my case, more recently from some of the others. But I still have fun with my 13-inch Dobsonian mount, one of those old Coulters. And other folks in the SETI group have telescopes as well. The SETI facilities include a few things that I think are interesting. The Allen Telescope Array was one of the major funding issues back in the early days of the project. It's located out in Hat Creek Radio Observatory, California area, a little bit north of San Francisco. They were going to try to put in 200 or so of these antennas, they call them. They're telescopes, radio telescopes, but they tried to put in a couple of hundred of them. But then when they found out what the cost was going to be per unit, they settled for 42. That's a big cutback, but it's still a very effective array, and it's been producing a lot of input, a lot of data, but nothing that would say there's somebody out there. But they monitor 72 million simultaneous channels, each one 1 kilohertz, 1 hertz wide. That's not a kilohertz, that's not a mistake. 1 hertz, 1 cycle per second wide. Each of those is considered to be a band unto itself, and they monitor 72 million of those simultaneously with that telescope array. There are other facilities, one of them being this one, which is the large array, the very large array actually, in New Mexico. And they brought this one on board. I'm not sure of the exact date, but they brought it on board so that they could have essentially full-time, 24/7, if you will, operation. And so they cover, in the case of the ATA, that one covers 1 to 14 gigahertz. The very large array covers from much lower, a couple of hundred megahertz up into the gigahertz range. They overlap a little bit in time and in frequency range that they can cover, and that gives them a little bit more capability. There's actually another one which is involved. I'll talk about that in a moment. One of the major efforts within SETI is the Carl Sagan Center. There are more than 100 scientists involved. I'm not sure the exact number right now. It varies from time to time, but they are funding a number of efforts in exobiology, in the search for the right way to communicate. Do you use AM? Well, no, because the scintillation in the cosmic background is so vast and so heavy that you can't get through. But how about phase modulation, frequency modulation, other techniques that may have a chance of getting through in the presence of a large amount of noise? The other thing that the Sagan Center does is this support for STEM, education in the science, technology, engineering, and math programs, and a lot of outreach in the same way that you folks seem to be doing from what I just heard a moment ago. The Drake equation is really what we're dealing with here. It was an attempt a while back to assess whether or not there's any life out there besides us. And so far, there are two extremes in assessing what this formula can tell you. In the most pessimistic case, it says we're alone. There's nothing else out there because all of these factors are working against us. Others are saying, well, that's not quite so. We've got telescopes now out in space with, all that have been launched over a period of years, including the most recent one. And so we have a situation now where we can say there are exoplanets. We know there are planets circling other suns, and, well, I shouldn't call them suns, stars. And they are, in some cases, they have atmospheres that they were able to detect, and there are techniques for doing that. And so they think that the percentage of possibly supporting life type planets out there is quite large. And I've kind of thought that all along, but that's just supposition on my part. But the real kicker is the L out here at the end. I don't know if you have the same concern that I do, but we have a tendency to try to blow ourselves up. And the question is, even if life gets to the point where they have intelligent life and the ability to transmit and receive, they may die off before they get to do anything useful or not exist at the same time as we are existing now, or in the future when we might be able to get a signal back from them. So that Drake equation is the thing we're struggling with. What I'd like to recommend here is if you want more information on the SETI Institute, just SETI.org will get you there. There's a revised version of the Drake equation, which is actually the one I was just referring to, that says the possibility of life on planets is fairly large. You can go to that. It's just basically science.nasa.gov and go to you can work your way down through the chain there and get to the thing that's talking about the Drake equation. And they show a modified version of it where it collects several terms together and shows more optimistic view of what we may find. And the third telescope that I wanted to mention is the one that is south of the equator, the only one. everything has been in the northern hemisphere so far, but now the Murchison Wide Field Array in Australia is part of the package, and they're doing SETI research there. Regarding the Denver area SETI group, if you want information on it, have any interest in joining, there are no fees or anything. It's just a way to get together and do like a book club, share views of films or live presentations that SETI does, and then maybe have a discussion group following that. So if you're interested in that this area down in the lower right-hand corner, it just tells you what our interest is. And we'd love to have you join us. And several of us, myself included, along with Ed and possibly two others, will be joining the Denver, the DAS. So anyway, that's it. If there are any questions or anything, I'll be happy to answer them. But that's the presentation.
Mehmet, are you ready?
Yes. Yeah, we are coming back to the solar system now. And we hope there is some intelligence life form here. Our topic of our guest presentation is understanding liquid stability across the solar system. And our guest speaker is Dr. Jennifer Hanley. She is a tenured planetary scientist at Loral Observatory at Flagstaff, Arizona. She graduated from Cornell University in 2006 with a bachelor's degree in earth sciences and received her PhD degree from University of Arkansas in 2013 in space and planetary sciences. Her current research focus is on investigating the stability and properties of liquids and ice at low temperatures and pressures, with relevance to the outer solar system, especially Titan and Pluto. She also studies the stability of water and ice on Mars and Europa in the presence of salts. So, Jennifer, please start your presentation.
Thank you. And actually, as an aside, I did spend 2 years in Boulder. I was a postdoc in between my graduate program and then coming to Lowell. I was at the Southwest Research Institute in Boulder for 2 years. And so I do miss the Front Range, and I'm really happy to be here speaking with you tonight. So yeah, I'm going to talk a little bit about liquid stability across the solar system, particularly things like water on Mars and Europa, as well as the very strange liquids on Titan. So starting with Mars, we know that there's ample evidence of past water. We see things like these streamlined islands where you can see the water was flowing from the bottom to the top of the screen on the left here, making this teardrop shape. And then on the right, the flow is actually in the opposite. So from top to bottom, where you have these dendritic river features. And you can see they kind of come down just similar to tributaries on Earth, where you collect more and more water into larger and larger river basins. Some more examples, these kind of meandering rivers. You can see this on the left, kind of a circular area where the water kind of collects like a little eddy and then goes around. Eventually this might get cut off. You see this a lot, on the Colorado Plateau, Grand Canyon, these kind of things where you get, Horseshoe Bend, for instance. And then there's also evidence of deltas. So this is on the left here, a really great example of a deltaic feature similar to, for instance, like the Mississippi River in New Orleans, where you have a lot of sediment and it's being transported by the river, and has some amount of energy and momentum. and it's carrying these sediments, and then it hits a stable or not moving body of water like a lake or the Gulf of Mexico. And then because the water slows down, it drops all of its sediment, and then you get this delta feature. And you can see similar zoomed in features on the right here, like a distributory fan. So we see all this evidence that Mars has had liquid water in the past, but right now it's not very conducive to liquid water. And that's because it's cold. There's not a lot of atmosphere. The atmospheric pressure is low, and the temperatures range from 120 Kelvin to maybe above freezing if you're at the equator at noon in the peak of summer. And that's really about all you're going to get for liquid water, pure liquid water on Mars today. And yet we see evidence of some sort of flow feature. An example of this is recurring slope lineae, so named because they recur year to year. They're found on slopes. So here on the right side of the image, you see a crater rim, and then the slopes are going from kind of the right to the left, and they're line-like features, so they're lineae, so recurring slope lineae. And there's been a lot of discussion over whether they could be liquid or dry flows. And one of the best things that we can do to start to understand whether or not they could even be liquids is study where you can get liquid on Mars today. And one way that we've done this is through the Phoenix lander. It landed in the North Polar region of Mars, and it has a unique instrument called the Wet Chemistry Lab, and this is the only wet chemistry that has ever been done on another planet. So we have the scoop that takes up some regolith, drops it into the little sieve here. You can see a picture of the sieve on the bottom, and then on the left-hand side, you can see the different cells. So there's 4 little labs where the regolith goes through. And then on the right, you see this little animation where you have liquid water goes in, it dissolves whatever is in the regolith, and ion selective electrodes will measure whatever is dissolved into the liquid from the regolith. And it was really interesting because they had an ion selective electrode that was meant to detect nitrate, which is a fairly common salt on Earth. And the signal that they got, there would have been more nitrate than there was sample. So they figured, well, that's clearly not accurate. And so looking back, they realized that the electrodes were also sensitive to other ions, in particular some oxygenated chlorine ones called perchlorate and chlorate. And so these are highly oxidized types of salt. So chloride is, of course, the chlorine that we're most familiar with here. That'd be, NaCl, table salt. Is just sodium chloride. You might see magnesium chloride, calcium chloride. These are all very common. Hypochlorite is very reactive. That's bleach. And then perchlorate you might have heard of before. Potassium perchlorate in particular is rocket fuel. So a lot of energy coming with these molecules, and they're fairly rare, especially on Earth. There's not been a lot of studies because they only accumulate in very, very dry regions because they're so soluble in water. So, we only really started thinking about these highly oxygenated types of salts when Phoenix discovered them. And salts can be really important for, understanding the actual stability of water. And that's because salts can lower the freezing temperature. That's the reason why You salt roads in the winter. So those tend to be a combination of magnesium and calcium chloride because they lower the freezing point below what the ambient temperature is, allowing the ice to melt. Salts can also increase the boiling point and lower the evaporation rate. So some examples of this. So a little bit of chemistry, some phase diagrams. Basically, on the left of each of these plots, you have temperature, and on the x-axis, you have different salt concentrations. And so the point of this is that you have liquid above, in the top part of the diagram. And then once you cross one of the lines, on the left, you get ice, and on the right, you get a salt to precipitate. And the lowest point is called the eutectic, and that's the lowest possible freezing temperature. You will have a very concentrated salt solution at that point, but it's, kind of tells you something about how cold you can get. And so, for instance, magnesium chlorate, you can get down to almost 200 Kelvin, which is, that's very cold, minus 70 Celsius we're talking about. And so it's really important to quantify and understand the salts that we have. Another thing I mentioned is that it lowers the evaporation rate. Here's some another example. So if you had pure water, that's this thick black line here. And then as you start to increase the concentration, the evaporation rate on the left drops. And so increasing the salt concentration as well as decreasing the temperature slows your evaporation rate. And this is all tied to something called water activity. And so this is a really useful concept because it actually makes it salt agnostic. Anything in solution will change the water activity. So on the right, you see this diagram where you have your water, and then your ions have dissolved, and you can see how some of the ions are starting to pull on the water molecules. And so really, you can think of this parameter as, 0 is no water, 1 is pure water, and anything in solution is inhibiting water's ability to behave like itself. So if you're below 1, then, you think about trying to freeze, and it can't order itself because things are interfering. Or it's trying to evaporate or boil, and again, things are interfering or holding them together in that liquid phase. And so it's also tied to the vapor pressure, basically, again, thinking about how much can exchange between the liquid and vapor phase. And that's actually where we get relative humidity from. Relative humidity is the amount of water that's, in the atmosphere as a percentage of how much the atmosphere can hold, or the saturation vapor pressure. So water activity is really useful, as I said, because it is kind of agnostic of what's in the solution. And so we can see that as water activity decreases, or I should say, as the salt solution increases, water activity decreases. And so this is an example where I modeled the ions that were found in the Phoenix wet chemistry lab. So, took that soil and dissolved it and measured the ions, and we have those starting on the left side here. We start with 1 liter, or 1 kilogram of water, and these are the initial concentrations that were measured. And as we start to evaporate the water, so as we go towards the right on the plot, getting down to 1 gram, 0.1 gram, 0.01 grams, you have the salt is concentrating. And then you notice that some of these salts have like a little notch here, and then they have a different notch. And so they're dropping down. And that's because the amount of that ion in solution goes away as some of the salt precipitates out. But you can see that the ones that are left are the chlorate. And there's a lot of magnesium in here, and as well as chloride. And so, and then again, if you're looking at the water tube, that's the thick black line. We start at 1, and, you really have to get down to very concentrated solutions, right? We started with a kilogram and we're down to, well, less than 10 grams is when you really start to see this dip in the activity of water. And you can actually relate this directly to the freezing temperature. So again, we have the activity of water on the right here. We start at 1. As we go down from 1 kilogram to the right towards 0.1 grams, you can see that on the left we have temperature, and we start at 273. And then as you go down in activity, you decrease the temperature, the freezing point, and all the way down to 50 Kelvin. Now that's very, 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 very little water left. It's almost not really water at that point. But it is really interesting to start to just figure out what the conditions are on these different planetary surfaces and whether or not it could even be liquid. And so if we start to compare, so salts and chlorine salts in particular extend the stability. As I mentioned, of course, we have the freezing point, 273, boiling at 373 Kelvin or 100 Celsius, unless you're in Denver, where because the atmospheric pressure is lower, it makes it easier for the molecules to go into the vapor phase. And so the boiling temperature is only 95 Celsius, which is why we have high altitude baking cookbooks. So comparing that to Mars, if we think just about pure liquid water, same freezing point, but because Mars's atmospheric pressure is so much lower, you really only have about 10 degrees of stability before it starts to boil off. However, if you take a concentrated solution of magnesium perchlorate, you can get all the way down to 206, as well as increasing the boiling point. So you're actually extending the stability range in both directions. Another reason that salts are really important is because they're very hygroscopic. So most of these salts really love water. You see obviously, if you have like salt sitting out on your counter, sometimes it might turn into liquid droplets. That's why they have, but they put grains of rice in salt shakers, sometimes in restaurants, because otherwise the salt will absorb and turn into all clumpy and everything like that. So, we can use this to our advantage if we're trying to actually get liquid water. Here is an example of this process. So it's a process called deliquescence. And this video is of magnesium perchlorate in our Mars chamber. So we're at kind of room temperature and room relative humidity. There is no liquid starting. There's just relative humidity. There's just 75% relative humidity. And over time, the perchlorate is so hygroscopic that it actually pulls water vapor from the atmosphere and dissolves into it and turns into a liquid. You can see that, we start out at the very white salt, and then from the right side of it, we get these droplets, and it's starting to really just dissolve the salt. And then if we actually think about whether salts, what that means for life, thinking about some types of organisms really like salts. So extremophiles or extreme loving organisms, there's a subset of halophiles, and that's salt loving organisms. So thinking about the lowest possible water activity, we're down to 0.585, and this is interesting because a lot of information about water activity and life comes from the food industry because they're trying to kill life. They do not want the life to, these organisms to replicate across their, whatever shelf-stable thing that they're trying to make. And so, they want to try and salt things and keep it out. And so, we're kind of coming at these from different directions. But as I mentioned, there are, sometimes these chlorine salts can be conducive to life because they have a lot of energy. We have seen studies in some of these cryo regions on Earth where a microbial community was even thriving in magnesium chloride-rich brines at low water activity. We've seen bacteria like actually being active down to 18% sodium chloride and -25 Celsius. And then I love this story. So in the background here is an image of some halite crusts. And this is there's these halite crusts in the Atacama Desert in Chile, right? This is one of the driest regions on Earth. And they have these salt crusts. And it really doesn't rain there because it's in the rain shadow of the Andes. And so a group of so Davila et al. And a lot of other researchers have gone down there as Mars analogs. And for a year, they monitored it to see when liquid water was going to form. And there was only one liquid water event in that whole year, one time where it rained, and there was actually, droplets of rain reaching the surface. However, they recorded 57 different times when the relative humidity reached above 75%, which means that these salts, especially the halite, because that's its deliquescence point in relative humidity, there's 57 times where the salts deliquesced or turned into liquids. And so these microorganisms actually live inside these halite crusts, and they use that liquid event, that deliquescence event, in order to get some more liquid than they would if they had to wait for pure water. And then, as I mentioned, there's perchlorate and chlorate reducing bacteria. So again, they use that extra oxygen as energy. So trying to figure out, okay, so we see salts can help us get to some amount of liquid on Mars. We look at hydrated minerals and where they've been found so far on the surface of Mars. If we look at, this green, which is hydrated sulfates, primarily those are the ones that have been detected because they were a lot of the ones that were in the literature, for reference spectra. And so we see a lot of variation, different other salts, carbonate salts, and other, phyllosilicates and things like that. But it's really important that we distinguish between, for instance, sulfates and chlorides or perchlorates because different salts have a different effect on water. And chlorides tend to have a lower freezing temperature, or the chlorine salts in general have lower freezing temperatures. So you can see here on the right, the sulfates are in red, carbonate in yellow, chlorides in green, perchlorate in green, chloride and chlorate in different blues. But you can see that generally the sulfates and the carbonates are up higher, with the exception of the iron. And the chlorine salts can also be a source of energy. And so to show this in a different way, we have this figure again, and we have so we're trying to really understand where these salts are located. I'm part of a project where we're trying to identify chlorine salts in particular, across the surface of Mars. A lot of the rovers have detected perchlorate and chlorate. But, kind of to summarize the Mars part of this, salts do extend the stability range of liquid water, and could potentially be the source of flow features such as recurring slip lineae. Salts do lower the water activity, which does affect habitability. It's kind of this balancing act where you want enough salt to lower the freezing point so you actually have liquid water, but not too much salt where you lower the activity so much that life can't survive in it. And so, like I said, we're doing a systematic search on Mars. So moving out into the outer solar system, Europa. So from the Galileo mission in the 90s, it mapped Europa icy versus non-icy. So as you saw from the picture, it looks a lot like just water ice, but there's some colors to it, right? There's some reddish colors. And you can see here that the dark, the black bands here in the black and white image correspond to this non-icy material on the right, which is the red. And further work using the Hubble Space Telescope has identified irradiated chloride salts, primarily in the chaos terrain. And so this is something we expect. Jupiter's environment is incredibly active, and Europa in particular is bombarded with a lot of ions and electrons and even like neutral particles. So it's just a very dangerous environment, especially for spacecraft. But so we do expect the chlorides to be radiated, and so we're looking in the visible wavelength region here. You can see that there's a color center band, around 450 nanometers, and this tends to be correlated again with these chaos regions, which seem to be the youngest terrain. We also see a correlation with chlorine salts using the Very Large Telescope. And again, you can see here, this is a map of Europa. So they basically had 4 little disks you can see overlaying the equatorial region, and then mapping through spectral modeling. You can see, so in some of these black outlines are the chaos regions. And in the trailing hemisphere is where you get a lot of the non-ice component and the magnesium and chloride and perchlorate bearing species. So something that I've been working on is using Lowell's Discovery Telescope. It's a 4.3 meter telescope here in Flagstaff, about 40 miles southeast of us. And I've used 2 different instruments, near infrared and the Extreme Precision Spectrometer Express, which is actually an optical wavelength spectrometer that is used to look for exoplanets. So it's very, very high resolution, and that they're actually trying to find, little Doppler shifts of planets around an Earth-sized planet around a sun-like star is the goal. But the really interesting thing is that we can use them on solar system bodies, and this is kind of a novel project because we're also using the Lowell Observatory Solar Telescope. So it also uses Express, and it looks at the sun every day for their own stellar solar, understanding solar variability, which hopefully will help understand stellar variability. But the cool thing for solar system science is that we can actually divide by the solar spectrum that we're getting with the exact same instrument. So we can start to, we don't need to take any standard stars or G2s or any comparison stars at night. So it saves us a lot of time. And, so here we can see some initial results from that. So we have the leading over trailing hemisphere, and you can see that comparing 2 different regions, 120 is the part centering on the chaos region. We have a much different shape when you compare it to the just kind of bland trailing region. And so it's really exciting. A lot of this is really still in progress, but I'm excited to see some more results for that, and kind of get an ongoing monitoring process in case there's anything like uh, potentially geysers or anything like that that could be giving fresh material, and we can just monitor it. Every semester we can get a few different observations on different hemispheres. And then if we look at the near infrared, you can see here again, we have crystalline water ice, very clear in the near infrared. There's this 1.65 micron feature, which is very well known to be sensitive to water ice at low temperatures. And then we see some other distortions here that are likely due to, well, that non-icy material, whether it's a salt or maybe hydrated sulfuric acid is another candidate. But again, just trying to start monitoring these things long term. So kind of thinking about how that all relates to Europa, the non-icy component likely includes chlorine salts. We've detected the chloride salts in the chaos regions. These are really important to understand ocean composition. And so, I mentioned how chlorides have a lower temperature. Well, so what that means for Europa is that the colder the subsurface ocean, the thicker the ice crust. And so again, there's this kind of balance between wanting to have liquid water and then also maybe wanting to have, a thinner ice crust where you can break through and exchange cometary material, organics, or things like that. And so, again, there's this balancing act on whether, what salts you really want to find. But again, we just need to go with what's there and modeling and just trying to understand what's really happening. Excitingly, Europa Clipper is going to be launching in just a month and will be arriving at the Jupiter system in 2030 and starting to take some more high resolution images and spectroscopy and other things. So moving on and outward to Titan, the largest moon of Saturn. It has a 1.5 bar nitrogen atmosphere. The lakes and seas are primarily composed of methane and ethane. So we have very, very cold hydrocarbon liquids. And so if we think about the surface of Titan only ranges between 89 Kelvin at the poles and 95 Kelvin at the equator. So it's a very narrow range of temperatures. But interestingly, that's right around the freezing point of methane and ethane. And so what this actually gets us is a very complicated methanological cycle, similar to the hydrologic cycle here on Earth, where we have liquid methane, you have evaporation and condensation into clouds, you have storms, we have methane rain, you have methane rivers, all flowing into these lakes and seas. There's evidence that the lakes and seas are potentially even connected, through some sort of aquifer or methanofer. So one thing that we're trying to understand in our lab is, well, just starting to mix these things and trying to really understand what happens, because especially at cold temperatures, not a lot of laboratory work has been done. And it's also possible that, some of these effects could explain the quote unquote magic island. So if we look at this inset area here, you can see that between 2007 and 2013, there's this extra bright region. It starts to go away in 2014 and it's gone in 2015. There's a few different possibilities, bubbles, waves, so it's probably not the case, ice, which is also very difficult to form, as I'll show in the next few slides. So it's not solved what it was, but you can see it's, kind of a big feature and something interesting going on there. I don't know, is the lake, maybe like an island came up, or the lake level went up or down, but it doesn't really appear that way based on other observations. So we're still trying to understand that, but that's just one example of the dynamic environment that we're seeing on Titan. So this is a time-lapse image putting together all three of those species, methane, ethane, and nitrogen. And so what you're looking at is a cell. It's about 2 centimeters in diameter. It's a cylindrical cell. And so on each end, we have sapphire windows that allow us to go in, look at the cell. And the cell itself is also about 2 centimeters in length. And so you can see here we're getting down to very, very cold temperatures before we even really start to see freezing. And then we see ice start to grow. We see some very, very bizarre features on Titan or in Titan-like conditions. Another example of that is we sometimes see, oops, go back, two liquids. So, so if we just look at on the left was, just kind of surface temperature, surface pressure, Titan. But if we were to go up to 2.5 bar, which is totally plausible if you think about how deep the seas are, they're on order of 100 meters deep. And so you can get up to 2.5 bar, considering the surface pressure is 1.5 bar. And you actually split into 2 liquids and a vapor. And it's just, you can see how the liquids are different here with the different shapes of the meniscus. You can see that there's a difference in surface tension between them. And it's just, it's so neat to be able to see these things, as you're doing the experiments. So to try and understand what's happening and like what's in one liquid or what's in the other, we have a Raman spectrometer. And so we have our 3 different bands here, methane, ethane, and nitrogen. And so the pure species is in the dotted line for each. So black for nitrogen, red for ethane, and green for methane. You can see that in the red spectrum, which is the vapor, we have some nitrogen and a little bit of the ethane and methane, right? So it's kind of all just, there's actually, it's all very low levels here. And then in the top layer, so our orange and yellow and maybe a little bit of the green, but so you can see these 3 here are all kind of grouped together. There's not as much nitrogen. And then here you have, a little bit more of ethane and kind of a medium amount of methane. And then as you get into the bottom one, which is the bluer colors, we start to increase the amount of nitrogen, decrease the amount of ethane, and decrease the methane a little bit. So the key point here is that both liquids have all 3 species. They're just in different ratios to each other. And so the bottom layer is a nitrogen-rich liquid that is more dense than the hydrocarbon-rich upper liquid. And it happens really fast. So if this is an example of where we start adding nitrogen into the cell, you can see that it dissolves into the liquid very quickly, right? You see the bubbles in the meniscus, you see these tiny little micro bubbles coming in, starting to mix with the liquid and form just, it's like starts to dissolve very, very rapidly. Another video is you can see here, so it's condensing in this vapor phase. It's condensing onto the top of the meniscus, but it's the nitrogen-rich, denser liquid. And so it drips from the top through the first liquid down into the bottom. And you can see the little like bubbles and the way the surface tension kind of holds them on top of each other. And we can also get interesting things like, see if we go to the next one. No. Ice forming. You can even get ice forming here at the interface between the 2 liquids. And so it's just like such interesting things, and we're trying to understand more. Here you can see as we're warming a little bit, you get nitrogen X solution, so you get nitrogen bubbles coming out. And so trying to come out of solution. So that could be one of the, the events that are happening where that magic island is showing up. So to briefly come back to phase diagrams and a little bit of chemistry. So we've done a lot of experiments in the lab. The gray dashed line is the binary of methane and ethane, and you can see that it follows that V shape, similar to how we saw water and salt earlier, which means that it's a eutectic system, right? It depresses the freezing point. And when we add nitrogen to that, that's the colored dots. And so it kind of follows the methane ethane line. And so if we have the methane alkane fraction here, that's basically 0 methane means it's pure ethane at this point, and 1 is pure methane over on this side. And so as you come down here, you kind of reach this plateau where you don't get you start to get something else. You either get a second liquid or 2 liquids and a solid. And that's because this is actually a 3-dimensional diagram that's been projected into 2 dimensions. And so we're changing the nitrogen content, even though we're keeping the vapor pressure at 1.5 bars. But as you change the methane fraction, more nitrogen can dissolve. And so you kind of have this plateau feature where we start to see the 2 liquids form. And so briefly, I just wanted to add a little bit about propane and some of the other trace species that we're starting to see on Titan, are starting to work with, that we know are present on Titan. Propane is the most common photochemical byproduct of methane in Titan's atmosphere after ethane. And it's very interesting to see how the different ices look different, right? So we have methane ice on the leftmost one, which is kind of opaque and amorphous. The ethane ice in the middle is more transparent and needle-like structure, whereas the propane is kind of in between, right? So it becomes more opaque as it builds up, but it tends to be flatter, more planar. And so actually, if we take this image on the right here, and so you can see here, it's just about 50-50 ethane and propane. If we add nitrogen, well, we can get 2 liquids again. And so there's another video showing as we're starting to add nitrogen, it becomes a very nitrogen-rich liquid, because neither ethane nor propane like to dissolve with nitrogen very much. You can see it's a very thick and very high difference in maybe density or some surface properties, because it's an actual ball at the bottom rather than a flat liquid. So we can see a lot of just interesting things. We have 2 liquids, vapor, and ice here. And then here's another image, again, just showing this one is like where it freezes across the surface. And so, I mean, I guess the big question is, do we think that this could even happen on Titan today? And at the current temperatures and pressures, we probably aren't getting ice nor 2 liquids. So if we're at, the surface pressure, you have to be down at 82 Kelvin, which is not the temperature. To be at surface temperature, you need to get down to 2.8 bar, which is actually possible. Again, we don't really know how the temperature changes with depth in the seas, but we do know that we can probably get to those pressures. And then, really, if you think about it, any kind of change will cause some amount of exsolution or dissolution. So imagine you have a nitrogen saturated methane raindrop, and it's falling, and it falls in this methane rich river. But you have a methane lake that has some amount of ethane, maybe even propane in it. And so kind of how we have that delta, flowing from with the sediments, it's kind of the reverse of that, where you have this methane rich, well, I guess you can consider the nitrogen to be the sediment in this case, but it's not soluble in the ethane and propane. And so as you have that river flowing in, you might get some exhalation of nitrogen that comes out. And so you might even have bursts or bubbles or something like that. So, just again, summarizing Titan, the mixture of methane and ethane will never completely freeze on Titan's surface. Even if we do start to see some ice forming, it'll never fully freeze because it's much below the temperatures that exist on Titan today. Mixing nitrogen can yield these two different liquid phases. And then as we add trace species, it just starts to get even more complex. If you think about that phase diagram I showed, and how we're already talking about 3 dimensions projected onto 2, then we start adding another concentration vector for the trace species. It just becomes a lot more complicated, but I'm really excited to see where we go with it. So I have like 2 little plugs. We are looking for graduate students at Northern Arizona University. So I'm at Lowell, but our Northern Arizona University is also in Flagstaff, and that's actually where our lab is located. And so there's a lot of different opportunities. There's master's or PhD, and then there's also opportunities for undergraduates for 10-week summer programs. And then we're also looking for our new prize postdoc at Lowell. So basically, you write a proposal. It's similar to like a Hubble Fellowship where you can propose to do some work, and then you get 4 years of funding to do it. And there's not too many strings attached to it. So, feel free to reach out, or if you know of any students or anybody else that might be interested in either of these opportunities, to give them my email. But with that, I just want to say thank you, and I really appreciate being able to speak with you tonight.
Thank you, Jennifer. This was very, very informative presentation. Let me start the questions, posing 2 questions,
Sure.
actually, related to Mars.
Yes.
You indicated that the increased salt activity or salt concentration reduces the water activity.
Yes.
So my first question is, are there any lessons or extrapolations for Earth on that? So that's the first question. The second question, what are the implications of that for the colonization of Mars?
Yeah, so let's see if I can get the that slide up that I want to show. So it's let's see if I can do this. Does that work? Nope. Okay. Well, I guess I will say okay, so as far as lessons for Earth, we've done a lot of studies on, the water activity. This is something that geologists and geochemists look at frequently, especially, and then also, as I mentioned, the food industry. And so, oh, here we go. Now I know. Okay, so if I come back over here, we can see that, here's a whole bunch of different research projects that have been done looking at salty solutions as well as water activity. And basically, we're looking at kind of limits on these. So the very lowest water activity we've ever seen any kind of microorganism live in is 0.585. On Mars, we have extra challenges. So it's not just temperature, not water, it's temperature in addition to water activity. You have radiation, a high radiation environment. So, we're still trying to figure out where or if it's possible on Mars, but we do see life in almost every single place that we look for it on Earth. And so, we see it in these glacial lakes underneath, hundreds of meters deep underneath, Greenland or Antarctica, and you drill down and there's microorganisms in them, even if they're very salty. And it's very interesting to start to try and test, these extreme environments. And there absolutely are people doing that. And then as far as colonizing Mars, there does appear to be a lot of salt, kind of just at maybe the 1 weight percent level in the regolith. So if we ever wanted to, farm on Mars, we would need to measure the soil, understand what's in it. Maybe do that wet chemistry lab again, where we try and understand what's dissolved in it, because if you start to water the soil, all those things are going to come out. And we actually know that perchlorate, as I said, is very soluble, and perchlorate is toxic to humans. And so if it concentrates, it can create thyroid problems. So we really want to make sure we're not uptaking, the perchlorate from the soil into our lettuce, which is something that takes up a lot of nutrients from the soil typically. So it'd be something we'd have to be very careful about.
All right.
Thank you.
Thank you. Let's take a question from the room.
Hi, interesting presentation, thank you. My question, probably a college chemistry course would answer for me, but propane and stuff like that you're finding, and methane and ethane on Titan is made by dinosaurs here. How is it from there?
I only heard, the propane and dinosaurs. So what was the question?
So the propane, ethane, and methane here is formed by dinosaurs. How was it formed on Titan?
Right. So that's actually a very interesting question. We are uncertain where the methane is coming from on Titan. The ethane and propane and the other higher order hydrocarbons are formed through photodissociation. So gamma rays or sunlight hits the upper atmosphere and it breaks down the methane and then reforms into these higher order hydrocarbons, the ethane, the propane, et cetera, all the way up to very thick things, including like tholins, which is these kind of like goopy hydrocarbon materials. But given that the methane is breaking down, all the methane should be gone by now. And we're not really sure where it's coming from. So a couple possibilities are that, it has to be primordial in some way, because there's no formation mechanism of the methane. So it's more like it's been sequestered and coming out possibly through like methane clathrates, which is, the methane gas is trapped in a water ice cube. Or it's possible that the atmosphere is not as old as we think it is, or that it goes through these kind of ice ball scenarios where because of orbital dynamics, it gets cold enough that the atmosphere condenses out and we just have like, solid nitrogen, ice and methane. And so you're not getting the breakdown throughout, the 4.6 billion years of history. Those are kind of the two leading theories as to why there is still methane there, but all the rest of them come from the methane.
Thank you. Let's take a question from the chat. I'll just read it out. Thank you for your interesting presentation. Will NASA's JUICE mission collect data from Jupiter and its moons to address some of the remaining questions about liquid stability?
Yeah, so ESA is the organization that sent JUICE. It launched last year or earlier this year, and it'll actually be arriving at the Jupiter system after NASA's Europa Clipper, just because of the launch vehicle it used. But so the JUICE mission is primarily focused on Ganymede, but it will be able to look at Europa and the other Galilean moons, and absolutely, this is kind of really the big push in going to the Jovian system, is looking at these different moons and just really understanding what that subsurface ocean is, because we're pretty sure that there's a subsurface liquid water ocean underneath the ice crusts of Europa and Ganymede. It's possible for Callisto, uncertain, but we're fairly confident about Europa and Ganymede. And so NASA sending one to Europa, the European Space Agency sending one to Ganymede. They will have the ability to look at both. In fact, NASA's Europa Clipper is not even orbiting Europa, it's orbiting Jupiter. And that's because of that high radiation environment I was talking about earlier. So it's actually going to be, in a polar orbit going around Jupiter, but it'll do these flybys of Europa, and it can go, inside or outside the orbit. And this will extend the longevity of the mission because it won't be fried in this high radiation environment as though it would if it was orbiting Europa.
Thank you. So if you're online, go ahead and raise your hand if you have a question, or go ahead and put it in the chat. This time I'm going to ask, is there anybody else in the room that wants to ask a question? Yeah. All right, Dr. Bickle.
Thank you. Very interesting presentation, Mr. Hanley. One question, I guess actually two questions. One of the things I have read is that the lack of geomagnetic powers like we have on Earth resulted in much of the atmosphere on Mars going away. And I think one of the questions I have is, was there more oxygen along with the water that apparently disappeared off of Mars at some point? Do we know that?
So we don't know that. You are right that the leading theory is that because the core of Mars, Mars as a planet is smaller than Earth, and therefore its core is smaller, it probably solidified, and it probably did have a magnetic field, a dynamo in the past. And then once that magnetic field, once the core froze, there was no more magnetic field, and then the solar wind could strip away the atmosphere. A big question is what that atmosphere was composed of. There are conflicting theories as to what the atmosphere was made of. Again, we see evidence of liquid water in the past, which means that at those large scales, they had to be, very, very close to pure, like Earth's oceans are only 4%, sodium chloride. And so it had to be very warm. And to get it to be that warm is a challenge, So one leading theory is that it was primarily CO2, a CO2 atmosphere, in which case there wouldn't have been very much oxygen at all. Another theory could have been nitrogen, in which case maybe there would have been oxygen, but mostly oxygen on Earth comes from life. And so it's unlikely that there was oxygen in any large quantity in Mars's atmosphere in the past.
Any follow-up? I'll take it. All right. Jan and Jim Wallace ask, can you tell us more about the chemical studies aboard the new mission to Europa?
Yeah, so it's going to be a really great mission. There are a bunch of different instruments. There is a visible camera with some amount of spectroscopy information. We're going to get some really high resolution images, and this is really going to help us because the chaos regions, they almost look like ice blocks where you could fit them back together. Let's see if I can bring it up. So you can almost see here how the striations look like maybe ice blocks got frozen in an ocean. And so we'll be able to get into much higher resolution. And then there's a near infrared, and there's also a mid infrared spectrometer on board. And that's going to be where we really get into the chemical composition of these of the surface, right? So this is how we're going to, look at the the spectral fingerprints that tell us what molecules are present. And then if there is some sort of plume or geyser, which has been suggested by Hubble Space Telescope studies, Europa Clipper can actually fly through it, and they have a mass spectrometer on board, so it can measure the molecules in that way as well. So, and then the mass spectrometer can also be used for the atmosphere, which is very tenuous. It's mostly just sputtered molecules off the surface, but it can tell us something about what's in the surface by measuring what's been sputtered off. So those are kind of the main instruments. There's also like a radar, or not a radar, magnetometer. So, and that'll help tell us something about, if there's salt in the ocean, which we're pretty sure there is, but it'll help give us some idea of the induced magnetic field from that.
All right, is there another question in the room? Does not look like it, so I'll go ahead and ask. Jan and Jim will also ask, what kind of chemical study would you recommend for a future Mars mission?
Yeah, that's tricky. I think, I don't know. So it's a really tricky question. I think that we have a lot of really great instruments on Mars today. I'd like to see more variety in locations. So most of the missions have gone to the equatorial region just because it's lower in elevation. It tends to be flatter. It's safer from an engineering perspective. We have gone to the North Pole region, but if we could try and get to the Southern Highlands, that'd be very interesting, or even landing on some of the poles and understanding the what the ice is composed of, and really trying to understand that. If you think about it, if you were to land one mission on Earth, and let's say you landed in the Atacama Desert, that'd be very different than landing in the Amazon rainforest, right? I mean, we can see these things from orbit, but to be able to actually dig into the variations across Mars, I think would be really interesting. So maybe not necessarily different studies from what's been done, but just a wider variety of geographic locations.
All right. I don't see any other questions. I think that's it. Thank you for your talk.
Yeah, thanks
Yeah.
for having me. This was fun.
Thank you, Jennifer. We very much appreciate.